Okay, I'm going to begin. So what we did yesterday was we sort of reviewed, first of all, I gave you the 4 fundamental forces before I do anything. Okay, so yesterday, at the end of the day, I created a Google document. You guys can't read that, can you? That has that outline. Remember the outline that I showed you? So it looks like this, and I linked to it. Right, here's the Google Doc. So what we did yesterday, identified the 4 fundamental forces of nature, and then in blue I wrote kind of like in English what I would expect to be able to do out of that. Can you read that? It says, know the names, a little bit about them, and their relative strengths. Okay? So you can follow along a little bit there. This will be our test outline. It'll be good for me because I can make the test right from this. And you can, if you want, because you have the link, it's right there, you can actually go in and you can add stuff in there if you want to. Something that I missed maybe. So why are you looking at me like that now? Why you would? Then I just do this, see revision history, and go backwards in time. I'll show you. Okay, so what I would like you to do today is you can work individually, you can work with a partner, or maybe a small group if you like. You have, I think, is there about 12 questions there, I think, something like that? Is 12 the correct number? 13? Okay, so you have 13 questions there. What we did yesterday was we talked about all 3 of Newton's laws. This one is strictly Newton's first law. Who remembers from yesterday what Newton's first law was?
Force will remain in state of rest or in motion unless force acts upon it.
You've got most of the correct words, Joey. Maybe not so much together in the right spot, but pretty close. Most people think that Newton's first law says that an object in motion, an object at rest. Okay, but we want to expand that a little bit, right? If there's no net force, then a stationary object remains stationary, or a moving object continues moving in a straight line at a constant speed. Okay, so all of these questions are really to see if you understand that, or if you actually believe it, actually, is a better way to put it. Okay, so I'm going to give you about 15 minutes to go through that, and then we'll go through them. Okay, go. Let's see how you did here.
Yeah.
Well, question 1 is a yeah. Does your device tell you how you did?
76%. 69.
Let's take several minutes and let's go through this. You have the handout. I would strongly encourage you to jot down the correct answer and maybe any supporting notes that would go with it. So, imagine a place in the cosmos far from all gravitational and frictional influences. Suppose that you visit that place and throw a rock. What will the rock do? Continue in motion in the same direction at a constant speed. Why doesn't that happen on Earth? Friction. Gravity. Is there gravity far in space? Oh, this actually says far from all gravitational frictional influences. So is there actual areas in space, like let's say between the Earth and the Moon, is there an area where there's no gravity?
No.
Yes.
Yes.
Yes, no, ooh. Jake really wants to say something.
Well, I don't know, I just heard there's a point where the moon's gravity and the Earth's gravity cancel each other out, and an object in that spot will just stay there forever and ever.
That would likely be true. But there is gravity between the Earth and the Moon. What do you think is holding the Moon in place? Earth's gravity. There's gravity all the way to the Moon. We'll talk about why the people in 0G appear to be weightless. We'll talk about that next unit. Correct answer is 1. Okay, now we'll get into a little bit more challenging question. A 2 kilogram object is moving horizontally with a speed of 4 meters per second. How much net force is required to keep the object moving at this speed and in this direction, no decimal place? And I see that many people likely answered 8. And why is that wrong? You just said it here. An object in motion will stay in motion. So how much force is required? How much net force is required? The correct answer is 0. 0 net force. The key word is net force. Does it require a force to keep something moving? Yes. How much force? Just enough to overcome. Starts with an F. Friction. Just enough force to overcome friction. But the net force, like if friction is, say, I don't know, minus 10 newtons, how much do you have to push the other way? 10 newtons. And what is the net force equal to? 0. The key is that it's net force. A force is not required to keep an object from moving, unless, of course, there's friction. The problem is that in the real world, well, there's always friction, right? Or just about. Mythbusters does a pretty good job of reducing it. Did anybody find the second part of that? Am I go looking for it? No? I forgot to go look. Okay, so Macintosh, pause for laughter, are arguing in the cafeteria. Mac says that if he flings the jello with a greater speed, it will have a greater inertia. Tosh argues that inertia does not depend upon speed, but rather upon mass. Who do you agree with and explain why? Correct answer? B. Tosh is correct. Tosh says that inertia does not depend upon speed, but rather upon mass. What you're thinking about is momentum, which depends upon speed. Inertia is simply how much stuff there is. Full filing cabinet, lots of inertia, right? Tiny little remote control, not so much inertia. Could both of them go at the same speed? Yes. Which one would have more momentum if they were going at the same speed? Filing cabinet, a lot big mass. Which one would have more inertia? Same. It's how much? Oh, sorry, not same. Which one would have more inertia? Filing cabinet, right? Bigger. Sorry. Yeah. I'm glad I read your faces correctly there. Yeah. Suppose you were in space in a weightless environment. Would it require a force to set an object in motion? Yes, of course it would. Very good, 100%. Forces cause what?
Motion.
No. Forces cause change in motion, which is acceleration. Forces do not cause motion. They cause acceleration. You don't need a force to keep something moving. It's really the same question that I'm asking over and over again, right? It's, do you really get it? Notice that there's not a lot of numbers here, people. You're going to have to get it. It's not just a number answer. Fred spends most of Sunday afternoons at rest on the sofa watching pro football games, consuming large quantities of food. And as a bit of an aside, last night I turned on TSN2 at 10 to 10 last night, and they've got CFL football on. I'm thinking, oh, this is weird. A football game on a Wednesday night. They're replaying the Bombers and Hamilton from last weekend. Exactly my thought. I'm the only guy in Canada tuned into this channel right now. And I'm about to tune out. Anyways, what practice, if any, does this have upon his inertia? Here's Fred watching the Packers play down here. What happens to his inertia if all he does is sit around watching football games and eating chips? Increases inertia. Increases his inertia. He becomes, what is inertia really? Well, it has to do with mass, right? But it's, think about, if something's got a lot of inertia, it's hard to accelerate it, either to get it up to speed or to slow it down. Okay, Ben Too Close is being chased, yes, pause for laughter, thank you, is being chased through the woods by a bull moose which he was attempting to photograph. The enormous mass of the bull moose is extremely intimidating, but if Ben makes a zigzag pattern through the woods, he will be able to use the large mass of the moose to his own advantage. Explain this in terms of inertia and Newton's first law of motion. So which one of these is most correct? The moose has more mass, so he has less inertia, so he is not able to make zigzags as easy. The moose has more mass, so he has more inertia, so is not able to make zigzags as easy. And it will not work. The moose is still able to make a zigzag pattern. Has anybody been chased by a moose before? No? I once came upon a moose on a trail once. I thought I was going to be chased by a moose. Correct answer? B. Very good. The vast majority of you got that correct. The moose does have more mass, so he has more inertia, not able to zigzag. Right? I like to think of this as the Titanic kind of explanation, right? Did they just sort of go crashing into the iceberg? Maybe don't know the full story. They actually saw the iceberg. They tried to move, tried to steer, right? But guess what? It's a big boat. It's got a lot of inertia. Is it easy to move? No. It requires a huge amount of force or a huge amount of time. And we'll get into impulse in grade 12, okay? Not able to make that zigzag kind of thing, right? When Riley's running up the middle, he's got, compared to some people, a relatively small amount of inertia. He can zigzag back and forth. I've seen him do it. Large linebackers can't do that. They can't catch it, and I've seen that too. 2 bricks are resting on the edge of a lab table. Surely she's short. Stands on her toes and spots the 2 bricks. She acquires an intense desire to know which of the 2 bricks are most massive. Since Shirley is vertically challenged and she's unable to reach high enough and lift the bricks, she can, however, reach high enough to give the bricks a push. Discuss how the process of pushing the bricks will allow Shirley to determine which of the 2 bricks is most massive. What difference will Shirley observe, and how can this observation lead to the necessary conclusion? So, which one is true? The brick that moves more has more inertia and is heavier. The brick that moves more has less inertia and is lighter. Both bricks feel the same, move the same distance. Hopefully nobody picked C. Oh, one person did. Correct answer? B. If you give 2 bricks a push and one moves more, then that means that it has less inertia and is lighter, because the same force causes a greater acceleration. Do you remember this one here? Acceleration is proportional to 1 over the mass. So if the mass is bigger, then the acceleration is less. So if you get more acceleration, then that must mean less mass. Good? Okay, now here's where things start to get interesting, especially with this giant cat.
Oh my gosh, the cues get better.
That cute?
Yeah, I love that cat. They're so awesome.
Okay.
Little ball, they roll.
A little ball.
Oh, well, yeah.
I think that one's been watching football games and eating food and increasing its inertia.
Looks like it right there.
All right, so the name here is, did anybody read it and figure it out?
Look out below.
Look out below, yeah. Look out below drops an approximately 5 kilogram cat, which has an approximate weight of 50 newtons. He's not a very nice man, no. Off the roof of his house into the swimming pool below. Upon encountering the pool, the cat encounters a 50 Newton upward resistant force, which is assumed to be constant. Use this description to answer the following questions. Which one of the velocity time graphs best describes the motion of the cat, and support your answer with sound reasoning? Is it graph A, is it graph B, or is it graph C? Who said A? You guys probably know whether you got it right or wrong already, don't you? Everybody say A? Why did you say A, Callie?
Yeah.
Took a guess. Okay, anybody say B? Quite a few. Zach, why did you pick B?
Originally dropping, and then both forces equal out.
Okay. Okay, and then anyone pick C? Okay, do you want to explain why you picked C, Liam?
Because it'd be going down, and then it would hit the water, and it'd slow down.
Okay. And do you know that the correct answer is B? The correct answer is B. Zach's reasoning is very good, right? The velocity of the cat increases as it falls in a negative sense. It becomes more and more and more and more negative. But when the cat hits the pool, I got 50 newtons of gravity weight pulling down. I've got 50 newtons of resistance, water resistance. And so what is my net force equal to? 0. And if there's no net force on a cat, then the cat will either stay at rest or continue on at a constant velocity. So whatever velocity he has reached becomes his constant velocity for the remainder of the time. Now, is that really what happens when you drop cats into pools, Liam? Have you ever dropped a cat in a pool?
So, Andy,
Would this actually happen? Well, it could if the weight of the cat was perfectly balanced by the resistance. I don't suggest that you attempt this. Okay, but that is indeed exactly what would happen. Liam's point is correct. The cat might float. I don't know if cats would float or not, but they might go to 0. But that's not what happens here. You have to read the numbers. Okay? Okay, so that might affect your answer here in number 9. Which one of the following dot diagrams best describes the motion of the falling cat from the time that they are dropped to the time that they hit the bottom of the pool? The arrows in the diagram represent the point at which the cat hits the water. Support your answer with sound reasoning. So is it A, is it B, or is it C? No, C actually, not whatever. C. Really? Oh, sorry, I looked actually here which one was most popular, but the correct answer is A. The correct answer is A. Why is it A? Well, because here the dots are getting farther and farther apart, indicating that the cat is speeding up, accelerating, and we now know that the cat should be traveling at a constant velocity. So, in fact, the dots should be the same distance apart, which is what's happening here in A. Okay? Good, Emily? Yeah? Several of Luke's friends were watching the motion of the falling cat, and being physics types, they began discussing the motion and made the following comments. They didn't jump in and save the poor thing, they just discussed the physics of the situation. Indicate whether each of the comments are correct or incorrect. Support your answers. Once the cat hits the water and the forces are balanced, the cat will stop. That, my friends, is false. Will the cat stop? No, the cat will continue at a constant speed. Don't worry, Hannah, this is just a story. No actual cats were harmed in the making of these slides.
Nobody likes Luke out below.
No, he's a big meanie. Somebody should report that guy.
Report him on the website.
Number 11. This is not last one, right? It's 13. Upon hitting the water, the cat will accelerate upwards because the water applies an upward force. False. The cat will not accelerate upwards. Upon hitting the water, the cat will bounce upwards due to the upwards force. Oh, Ryan has a question.
Does the law, Newton's third law, that is equal and opposite reaction, right?
Yes.
That's Newton's third law. When the opposite force cause an upward acceleration, it may not be significant, but it would cause some.
This is always a stumbling block, this question. Is there a change in the velocity?
Well, upon hitting the water.
Not you, a 50 Newton fat cat, where it's perfectly balanced like that.
If it's perfectly balanced.
Is there, I don't see, and this is always the discussion here. We quite often run into problems here, and every year I go, oh, here comes question 11, the one where some kid asks a question that I don't know the answer to. Is there a change in velocity? I don't think so, right?
But if this is real life,
Yeah, but it's not real life, it's physics. Right? Is there a change in velocity? No, the velocity stays the same. So I think the acceleration must be 0. Having said that, I have a hard time saying, well, there's now a force acting on it and there's a mass, right? So there would have to be an acceleration. We've got a bit of a conundrum here. I think that maybe what I should do is probably get rid of that question because it makes sense here. Really what they're getting at here is that if the forces are balanced then it remains, the object continues moving at a constant velocity. I'm not going to disagree with you, Ryan, too much. I'm still working that one out in my brain. Every year I say that. Is that a good enough answer for you?
Yep.
We did this one, right?
No.
I think it's false, right? Yeah. Cat will not bounce upwards.
It'd be fun to see.
It would be, especially that one there, right? Okay, if there's anything that you're going to learn in the last 45 minutes, it's this statement. This is it. Okay, if there was a drummer in here, I'd ask for a drum roll. If there was a drummer in here. If the forces acting upon an object are balanced, then the object, A, must not be moving, B, must be moving with constant velocity, C, must not be accelerating, or D, none of these. What people say, it's probably 25% each one. Yeah. Correct answer is C. Must not be accelerating. Now, allow me to explain this a little bit. If the forces acting upon an object are balanced, 50 newtons one way, 50 newtons another, then the object must not be moving. Is that true? Could it be moving?
Yeah.
Sure it could. It could be moving at a constant velocity. But must it be moving with a constant velocity?
What if that constant velocity is 0?
Yeah.
Moving. Can you move at a velocity of 0? Says the lawyer in me.
Strictly no.
No. Okay, so it could be moving. It could be stopped, right? So neither one of A or B can be correct, so C must not be accelerating. Either continues at a constant velocity or remains motionless. That is the big one right there. Okay? Objects don't need motion or don't need forces to continue moving unless there's friction. Newsflash, there's always friction. Good?